suppose you want to simulate a continuous time Markov chain on your computer. Here are some tools. Basic one is called inversion sampling. So this is a way to, in principle, sample any random variable x with a cumulative distribution function f. And you need to do two things, so two steps. One is you draw a uniform random variable in 0, 1, great. And then you evaluate the inverse of the CDF at this u. So when I say, you can essentially simulate any random variable like this, it presumes that you can actually compute this inverse function. But as long as you have the inverse of f, all you need to do is evaluate it at u, and that's your sample of x. So let's see an example here. Here's a CDF of an exponential random variable with rate lambda. You can very easily verify this is the inverse. Here's how you verify it. This would be the relationship, and you can check it for these formulas. And then immediately from this, you get that this expression here, where u is a random variable distributed on 0 to 1, this random variable here is a sample of an exponential of rate lambda. Here's a picture of how this works. This is taken from Wikipedia. They call it inverse transform sampling. I called it inversion sampling. It's kind of similar. It goes by a few different names. You can see that the CDF is an increasing function, which is what it is. Its range is 0 to 1, so there's the range. And it makes sense from that standpoint why we draw a uniform random variable. It's on 0 to 1. And so we've drawn it here, and now it's kind of gets projected onto the x-axis. So it goes like this, right? And then down, and then here pops out your sample x. And then you keep generating, let's say independent uniforms, and that continues to give you independent samples of the random variable x. So pretty simple. Here's a quick description going through the calculation on the previous slide. And the one other thing I want to mention, and as far as inversion sampling, is how do you do this for discrete distributions? So it has a very similar theory to it, but you kind of have to implement it a little bit different because of the discrete nature of the set or the random variable. So this would be your set. So it's, I've labeled it here as points x1, x2, x3, and so on, possibly infinite. And we're going to take a random variable x on the set S. So this is a discrete random variable, and we're going to give it a distribution pi. So pi xi will be the probability that x takes the value xi. So similar to before, we're going to need a CDF, a cumulative distribution function. So we're going to have to sort these. These are kind of points on the x-axis. And as these points move to the right, the CDF should increase, right? If the CDF, a cumulative distribution function, is something that's always increasing. And this is exactly what's happening here. I'm slowly adding to it the probabilities of each point, each of these xi's. And then the rest is pretty similar. I'm going to have this convention here where fj is just the cumulative distribution at point xj. And then f of 0 is going to be 0, which is the starting point for any cumulative distribution function. Now draw a uniform, same as before, and then all you need to do is find which the interval to which it belongs. There isn't going to be an inversion like this happening, because in the discrete random variable context, the function f is going to be discontinuous. And so what we're going to do is look for the interval into which the random variable u falls into. And once you find it, you know that the corresponding value is your sample of the random variable. So in here, my u happened to fall, let's say, in between fj minus 1 to fj, then I know that the value xj is my random sample. And so these are the two basic applications of inversion sampling that you need for CTMC simulation. And I'm going to quickly go over how we do this. So there are two ways to construct a homogeneous continuous time Markov chain. One of them, as we know, is through these transition probabilities, which are specified for every single state in every single time, right? So you're given a transition probability from state X to state Y in some time t. And the second way that we saw, which is a little bit more intuitive, is the one that uses exponential waiting times and rates. So every state has a rate. We wait in that state for an exponential random variable with that rate, and then we transition according to this embedded chain. So there's an embedded chain with transition probabilities bxy, and that one tells us where to go. Right? That's the picture below me. Every single step is exponential, is of length that's an exponential random variable, and then every single switch is guided by or governed by these one-step transition probabilities for the embedded chain. And so not surprisingly, this leads to two ways to simulate a continuous time Markov chain, and I'm mentioning one little caveat here. So here I'm talking about homogeneous chains. We know what those are. Those are the ones that if you simulate them on any time interval, you can move that any interval anywhere you like, and the behavior doesn't change, right? So as long as the length of that interval stays the same, the dynamics proceed in the same way. When X is not time homogeneous, then you have to take into account the starting point. You can see here I've labeled my starting time here as S. We started at state X, we've gotten to state Y, and this happened at time T. And so it's a more complicated object, but roughly the same idea. And then in the second definition, the tweak is to take this rate, which is a number typically for homogeneous chains, and replace them with a function. So you have kind of an instantaneous rate at any single point in time. And like I mentioned, these two definitions should yield us two different ways to simulate a CMTC. Let's look at how this works. Here's method one. We're going to take time, which is what we start with. We're going to discretize it. And here, I'm kind of proposing for you a simple discretization, which is called uniform spacing. In other words, I'm going to take the value tk, this is a timestamp, my kth timestamp will be at k times h. So you're kind of taking up time and you're partitioning it into little intervals of length h, and you're stacking them up on each other, right? And so here time moves almost kind of in a discrete way, right? K equals 0 gives you time 0, k equals 1 gives you time h, k equals 2 gives you time 2, it gives you time 2h, and so on. And then what we're going to do, we're going to use this transition probability, the one that's specified for all states and for all times, and we're going to sample, right? This thing is discrete, right? The state space, this type of state spaces that we're considering are discrete. And so this is a discrete distribution. So I've already given you a recipe for how to sample from that. Sometimes there are built-in routines. Usually you might want to use those, in fact. In the case of time inhomogeneity, right, you just want to take into account the beginning and the end point of the interval over which you're sampling. So whereas in here, I've listed the distribution that would depend only on the length of the interval, which is h. Here I'm actually specifying the beginning and end point of the interval, but same idea, right? Here's an example. So xtk is going to correspond to a value xk. And suppose we start at, let's see, I'm starting at x0, which is equal to 2. So you can kind of imagine maybe the picture below me starts out at the value 2. And in that case, I'm going to sample from P0. So P0, you can see it's the probability distribution for the very first interval, right? The one that starts at 0 and ends on H. And suppose that when I sample this thing, I get 2 again, right? Which is likely going to happen because these, the continuous time Markov chain looks like a step function. So we're going to have to stay on the step for a little while before switching over, right? And here I've kind of listed all of these times. We kind of keep repeating this procedure and we keep staying on the step. So we keep sampling 2 again, and then sample the value 2 again, and 2 again, and 2 again. And then all of a sudden, at some point, we're probably going to switch. So kind of like in the picture below me, I switched over from 2 to 1. That's, the picture probably doesn't reflect that very well. It looks more like 3/4, but no, 1.5 or something. So in any case, you see the point here. Here is kind of what your simulation is going to look like. uh, these little points are samples of the continuous time Markov chain, and they happen over this grid with spacing h, and you're going to sample these points, and this is the kind of path that you're likely going to recreate. It's not ideal because you could be missing things, right? Kind of like there's these spaces, these gaps everywhere, and you sort of maybe don't know. Maybe there was a switch of a state there, right? It's possible, and possibly could have happened. And what you could do on one hand is to reduce the discretization spacing. You could take h to be a little bit smaller, right? And then you get kind of a more resolved path, right? The higher resolution, so to speak. And so this method, for the reason that we're seeing here, because you have this resolution issue, is not ideal. I'm going to give you method 2, which corresponds to the second definition, which I prefer. It's the one with rates at every single state, and it's super easy. So all you do is, you're always going to be at some jump time. This is the benefit of this thing. You're going to be kind of moving not in little increments of size h, but you're going to be moving in whole steps. So you're at some time tk, right? You can look at the picture below me again as a guide. Let's say we're at t1. The next time we're going to simulate is t2. And how do we do this? Well, it's just an exponential, and it has the rate belonging to that state. So if I'm in state xk, well, my rate is then rxk, so I just need to generate an exponential, which is the same thing as generating a uniform, right? We saw that from inversion sampling, and that gives me the length of this step, right? If I'm at t1, then the length of that step is given by tau 1, and then I just add it to get to tau 2, or in general to tau k plus 1. And then the next thing to do is sample from the embedded chain to get the next location. So at t1 we were in state y, it looks like in that picture, and at t2 we're gonna sample from b, and it looks like we're gonna get the value z, right? And again, b here is a discrete distribution. You know how to sample this. So quick note on time in homogeneous chains. This is a little bit more complicated, so don't worry if you don't follow it. But this was the distribution of the waiting time for an inhomogeneous Markov chain. In other words, instead of this quantity being e to the minus rxk times the t, it's this here. So it's a little bit more complicated. But what it is still a CDF, right? That's the key feature, is that this is still a CDF, and now you can use inversion sampling. So what I've done here is I've drawn a uniform, and I've essentially kind of partly inverted it. And now what you get by setting this quantity equal to u, my writing is terrible, but there it is, it's equal to u, and then I just partially solve it, and now my goal is to solve for this eta here. This is going to be my tk plus 1. And so obviously, kind of like you need some sort of numerical method here. This could be a complicated integral, but skipping the details, if you do solve for this eta, you have the next jump time, and you proceed to sample the next state. This is always simple, even when the chain is time inhomogeneous. The changes of state are super easy to get, right? It's kind of like inhomogeneity always makes you work only to get this waiting time, which is just not sort of a simple exponential random variable. Right, and here I'm just kind of being a little bit pedantic. If rxk is constant, then you obtain, from this equation, you obtain this, which gives you exactly what you would expect to sample an exponential, right? This rxk gets divided up here, and you get exactly the same formula that I had started with. Here is what the simulation would look like. You would sample you'd be at time 0, you sample an exponential, and now you get to t1, and then you sample from the embedded chain, and you get the next change of state, and then you sample the exponential to get to t2, sample the next change of state to get to state z, sample the next exponential to get to t3, then sample the embedded chain to get to state u, sample the exponential to get to t4, and so on. You get the picture, and so this is a much more preferred way of simulating a continuous time Markov chain.